Welcome to AP Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at our second set of notes from Chapter 17 dealing with buffer systems. Now, buffers are solutions that contain a weak conjugate acid-base pair. So you not only have a weak acid, but you also have a significant quantity of its conjugate base. And what happens when you have that type of system is its resistance to change in pH for both acids and base addition. So a buffer literally buffers you or protects you from changing pH. And this is incredibly important in certain body chemistry situations, inside aquariums where the fish need a certain pH to live and be healthy, as well as in pools where humans are swimming and need a certain pH to be healthy. So there's a number of different situations, in particularly body chemistry situations where buffer systems are critically important. It's very vital that we maintain a very specific pH in order to stay healthy. So how do we create that situation? Well, we need a significant quantity of both an acid. So here's a general formula for the weak acid HX undergoing hydrolysis to form H3O plus and X minus. Now, if I just throw HX in water as a weak acid, I don't get very much X minus. So while I have an acid to neutralize the addition of a base, I don't really have much base to neutralize the addition of an acid. I don't have a buffer system. So I need something that contains a lot of HX, our acid species, to neutralize OH minus, as well as a lot of X minus to neutralize the addition of H plus. How do I get that type of thing? Well, the easiest way to do it is to have a weak acid or a base that is in water and then add a salt that contains its conjugate. So I'm literally adding that conjugate of that weak acid or base. Doing that, I get a significant quantity of H. I've got a buffer system. Good example of that from an acid and a base point of view here. Acetic acid is a common weak acid. It's vinegar. If I add sodium acetate, not only do I have the weak acid in significant quantity, I now also have its conjugate base acetate in significant quantity. If I want to protect a base, then I get something like ammonia, which is a weak base. Well, if I add ammonium chloride to ammonia, I not only have the weak base, but now I have a significant quantity of its conjugate acid. Just throwing in ammonia in water won't do it because I get very little ammonium created. But if I add ammonium chloride, now I've got a significant quantity of each. That's the simplest way to make a buffer system. Now, a way that is a little bit tougher to see that you're creating a buffer system, but you do need to understand it for my test, or the AP test, is partial neutralization. You not only can create the system by just adding both, but if you half neutralize or partially neutralize our weak acid, it gets converted into its conjugate base, and now I have a significant quantity of each. So let's look at that situation. Here is a buffer system with acetic acid, and I'm going to form its conjugate base in significant quantity by neutralizing it with a strong base. Now, reactions happen at a particle level, so let's start by looking at the reaction. So we have acetic acid. It's reacting with NaOH through neutralization to make sodium acetate and H2O. I'm neutralizing my weak acid. Now, what you need to understand is this neutralization is taking my weak acid and converting it into its conjugate base acetate. So if I take 32 milliliters of 0.5 molar acetic acid, and I look at how much H plus that would give me, that's 0.016 moles of H plus. I've got a quantity of H plus. But if I just throw that in water, I have very little acetate that gets created. Well, when I add a small quantity of NaOH, so 8 milliliters of 1 molar NaOH would give me 0.008 moles of OH minus to neutralize. Now, H plus and OH minus neutralize to make water on a 1-to-1-to-1 stoichiometry. So by exactly how much my H plus is going to go down, I'm going to create the exact same amount of water and the acetate anion in this case. So notice I have exactly half as much OH minus, so I'm going to half neutralize my acid and make an equal quantity of its conjugate base. So in the end, through half neutralization or partial neutralization, I now have a significant quantity of both. So I can partially neutralize a weak acid with a strong base. I can also partially neutralize a weak base with a strong acid. The key is you have to partially neutralize it. Now, when you look at this situation, you may realize the other way to make through partial neutralization is if I add a salt like sodium acetate to water, I'm going to have a significant quantity of acetate, which is a weak base, and very little of its conjugate acid. But I can partially neutralize that weak base by the addition of a strong acid, and I can also make a buffer system. So it's the same idea, but now I'm starting with my conjugate base from a salt, and I'm adding an acid to partially neutralize it. So here is my sodium acetate thrown in water. I end up with a lot of acetate, but I really have very little acetic acid. Well, if I partially neutralize that acetate with the addition of a strong acid HCl, it's going to convert some of that acetate into acetic acid. And therefore, after I partially neutralize, I'm going to end up with a significant quantity of each. So you can really get to a buffer system three different ways. Literally adding the two things together, weak acid and it's a salt that contains its conjugate base, or through partial neutralization of either one. Now, understanding buffer systems and how to calculate their pH and what pH they protect, you really need to get into the equilibrium math. So let's go back to our general equation here for the buffer system of a weak acid HX in water. And after the addition of a salt that contains X minus, we now have a significant quantity of each. We have a buffer system. But it's an equilibrium system from this equilibrium reaction, so this is still going to be true. After I add the MX to generate more X minus, yes, that's going to knock me out of equilibrium, but eventually I'm going to get back to equilibrium, and at that point I'm still going to equal Ka through this expression. So the equilibrium expression for the Ka of this acid system would be this. Now we're really looking at what's the pH of the system. So we're going to rearrange the equation a little bit and look at what the H3O plus would equal. Now from this point of view, it's a little bit easier to see the two things that affect a buffer system. One would be the value of Ka. So change the weak acid, you change the Ka, that changes the pH of the situation because it changes the H3O plus. The other factor would be the ratio between the acid and the base, because HX is our acid, X minus would be its base. The ratio between those two things also has an effect on the H3O plus. Now, when we have a weak acid system, we can't change the Ka, but we can play with that ratio. Now, the optimum situation is when we have an equal amount of each. So we start with equimolar, and therefore the ratio is going to equal 1. So literally our Ka is going to equal our H3O plus. Well, if we add a little bit of OH minus, that's going to neutralize this a little, creating that. So this value is going to go down a little bit, and this is going to go up a little bit. But that ratio still is going to be relatively close to 1. So while I am neutralizing and converting one into the other, the ratio doesn't change appreciably, and therefore our pH isn't changing all that much. Now the problem is if you change that ratio too much, like more than a factor of 10 different, then it's no longer going to buffer the system and we stop protecting pH. So there's a limit to how much we can actually change that ratio. And remember, if we add H plus, it's just going to be the opposite. We're going to reduce our X minus a little bit, making HX, so that's going to go down a little, what's on top goes up a little, but the ratio still doesn't change a lot, and therefore our H3O plus hasn't changed a lot. So to actually do the math, what we're really looking at then is the equilibrium expression of our equilibrium situation, and we're looking at it from the H3O plus point of view. So we take our Ka expression and solve it for H3O plus. Now in this form you can see I've actually substituted in the words acid for the acid and base for the base. So you can see it's really the ratio of the acid to the base times the Ka that's going to equal our H3O plus. Now, before we get into doing a problem, one thing you should understand is what happens when we change the acid and the base from equal to each other. So let's start with what's called the equimolar situation. If the concentration of my acid and base are equal, then that ratio equals 1, and H3O plus is going to equal Ka. So literally the pH of that buffer is going to equal the pKa. The negative log of the Ka is going to tell us what the pH is. And when we add an acid or add a base and neutralize the other, one's going to go up and one's going to go down, so they're not going to be equal anymore. And we can see exactly what happens to the pH in those situations. If we neutralize the base a little bit, creating the acid, our acid concentration is going to be greater than the base concentration. Our ratio is going to be greater than 1, and therefore our H3O plus and our pH are going to change. So pH in this case would end up less than pKa. Now, if the base concentration ended up more than the acid concentration in this ratio, then the exact opposite would happen, and the pH would be greater than the pKa. And if we add enough of an acid or base to neutralize, and this ratio is off by more than a factor of 10, then we can't buffer anymore, and adding a little bit of acid or base will cause the pH to rapidly change. So as long as they're within a factor of 10 of each other, they will buffer the system. They will prevent pH changes. Now, one of the things you need to be able to do with the buffer system, besides understand how they're made and how they buffer, is to be able to calculate the pHs of them. Now, when it's equimolar, it's easy, because the acid to base ratio is 1 and the Ka equals the H plus, and therefore pH equals pKa. But when they're not equal, how do we do the calculation? Well, it's the exact same equation. So we've got this equilibrium system. This is the equilibrium expression. We rearrange it to calculate for the H3O plus, and at that point, we can plug in our values, take the negative log of them, and we can calculate the pH. So if that is the Ka of our acid, and our acid's concentration was 0.12, our conjugate base concentration was 0.10, it's quick math to see what the pH is going to be. In this case, it's 3.77. And remember, as a buffer system, I can add a little bit of acid or base, and that pH is not going to change all that much. That's what we're going to look at in the next set of notes, is how you would recalculate. Today, the only other thing I want to mention about buffer systems is this thing called pH range, and how we pick a specific buffer system to protect a specific pH. Now, the range of pH values over which a buffer system works effectively is called the pH range. And remember, equimolar is the ideal. So when we're equal amounts of the weak acid and its conjugate base, we're at our maximum ability to buffer the additions of acids or bases and prevent pH changes. And remember, at this point, pH equals pKa. Now, Henderson-Hasselbalch is an equation it talks about in the book. It's another way to do these calculations, but I think it's easier just to use our same old equilibrium math. So the math we're doing is the same as it's been for the last 2 chapters. Now, the thing you need to understand is the impact of that statement that I made, that when the ratio is off by a factor of 10 from equimolar, it stops buffering. Well, in pH, a factor of 10 is a change in 1. So our pH range for anything would be plus or minus 1 of the pKa, because at equimolar, the pH would equal the pKa, and all we can protect is plus or minus 1 from that value. So how do you choose an appropriate buffer system to protect a specific pH? Well, you've got to look at the Kas and what their pKas would be. So in the case of lactic acid with a Ka of 1.4 times 10 to the negative fourth, the negative log of that would be 3.85. So 3.85 plus or minus 1, I can protect with a lactic acid sodium lactate buffer system. Well, if I have a different weak acid, then I'm going to protect a different region on the pH scale. So let's say I have carbonic acid with its Ka of 4.3 times 10 to the negative seventh. The negative log of that is 6.37. So here I can protect a pH range that's a little bit more basic. And in this buffer system, I can keep that pH within plus or minus 1 of 6.37 before my buffer system is blown and it no longer protects. Now, if I wanted to protect a basic region, then I would take a weak base and find out its Kb, take the negative log of that, and you would see what you're going to protect once you convert that into a pH. And that's it. That is our second set of notes dealing with buffers.